So this will be our second kind of set of lectures on momentum equation. Very quickly, if we want to review what we saw before, the momentum equation, we start with Newton's second law. F, resultant force, is equal to ma, mass times acceleration. And we applied this to a smooth channel with mild slope. Um, the left-hand side is difference in pressure, force, hydrostatic force, and right-hand side is the rate of change of momentum. And then we just plugged in some values. This is the general form for not not only rectangular, in general form for any shape really. So that's why it's the generic form. And then we did a little bit of calculus, and we ended up with a term called the specific momentum, capital M, which I have on the screen. Obviously, you can simplify this to rectangular channels, and you're going to end up with a simpler equation, and everything is kind of translated into a small q. But this is, again, general form for non-rectangular ones. So yeah, for rectangular channels, if you do the math, very simple, couple of steps, and we can get the specific momentum for rectangular channels. Just keep in mind, this is the specific momentum per unit weight, per unit width for a rectangular channel. So width and weight are kind of divided and taken out of the equation. So whenever we want to look at, let's say, force, we need to keep that in mind. That has to be multiplied by gamma and then width of the channel. Okay, so that's what we saw before. Now we're going to continue on this idea of momentum and look at it from a slightly different application. So what we did last time was we looked at basically two cases. The first one was when we have an obstacle in the flow, and we want to look at the force. So that was when you have something like this. That's a open channel flow, and we have an object, whatever it is. It can be a weir, it can be step, it can be a gate, anything. And we said, okay, in a case like this, if that's a water level, we go from section 1 upstream to section 2 downstream, and there will be a force applied on the object. In reality, we're looking at the force applied by the object on the control volume of the fluid, but they're the same magnitude, opposite direction. So yeah, nothing complicated. And then we looked at this and we said, okay, in a case like this, the force divided by gamma is equal to the change in the specific momentum. So whatever we had upstream minus whatever we are left with downstream, m1 minus m2. That was case one. Case two, again, very quickly, we looked at this in a hydraulic jump. So a hydraulic jump, again, a quick section looks like this. Depth goes from supercritical to subcritical, something like that. And we have, again, we have section 1 with specific momentum 1, and section 2, specific momentum 2. And the difference here was that there's no object, there's no obstacle, so PF is 0. So the left-hand side of the specific momentum equation is 0. As a result, the specific momentum is conserved. So M1 is equal to M2. And again, if you recall, we used this and we said, okay, we did a little bit of math and we ended up using this equation to calculate what we call the conjugate depth. Conjugate depth. And what are conjugate depth? They are the two depth corresponding to a hydraulic jump upstream and downstream. One is supercritical always, and the other one is subcritical always. Right? So that was the second application of the momentum equation. Today we're going to look at the third application, and it's friction and resistance and bed shear stress and so on. So in this case, we're looking at a scenario where that's our channel, and we have water level up here, and we have a flow of, let's say, Q in this channel, and we have a friction force or shear stress acting on the wall. So tau. And we know that friction is always against the motion. So if flow is from left to right, shear stress or shear force will be right to left. So let's look at this and see how we can, again, use the momentum equation idea and study this kind of flow. If you remember, the general form of the Newton's second law left us with this equation that I have on the screen, equation 1. And And that's where we started to look at specific momentum. We're going to make a couple of assumptions for case 3 for resistance. First of all, we're going to assume there's no obstacle in the flow. So PF is 0. Okay. And then the second assumption is that we're going to assume we have uniform flow. Uniform flow, we defined it, we looked at it. It's a type of flow in which flow properties do not change with space, with distance. If the width of the channel is constant, which is what we're going to assume, so width of the channel B is constant, then it means as you go from, let me sketch a tiny section of a channel here and label our flow. So that's water level. And we are going from section 1 to section 2. Okay. In this case, if the width is constant and we have uniform flow, we know that that means depth should be the same. Y1 should be equal to Y2. And also, remember the force that we have in our momentum equation, the one on the screen, is the hydrostatic force applied by the water, by the fluid on the control volume, F1 upstream, F2 downstream. If the depths are the same, Y1 is equal to Y2, then these two forces should be the same because they're basically 1/2 of gamma Y squared. If Y is the same, then F will be the same, right? So that's one. The other thing that we know is that if Q is constant, which is what we're going to assume, then width is the same, depth is the same, everything is the same, so velocities will be the same. There is no reason why velocities should change. Okay, and if velocities are the same, look at our equation. The right-hand side will be 0. So this means the sigma fx in the direction of the flow will be 0. So right-hand side, 0. Left-hand side, we just saw PF is 0, so this term is 0. And also we have F1 minus F2, and F1 and F2 are equal. So these two will also cancel. So F1 and F2 are gone. And what that means is that we are left with two terms. We are left with, I'm going to move one to the other side. So we have tau times L, the friction force, equals W times sine theta, the component of weight along the slope, along the angular slope. Let me actually highlight that theta is this angle. That's theta. Okay, so we have weight in this direction, W sine theta, and then we have the friction force, which is distributed along the bed. So let's show it like this. That would be tau times L gives us the total force, and L is this distance. Okay, so in this case, case 3, with these assumptions, we are left with basically two terms only. Everything else is 0, cancels out. And it gives us friction force is equal to weight along the channel. Now, what does it mean, and what is it telling us? It's really saying that the driving force, which is weight, gravity, is equal to the resisting force, which is friction, tau times L. That's what it says in terms of physics, right? It says that these two should be balanced. So we're going to look at this in a little bit more detail. But before we get there, let's summarize. So what do we see? I'm going to write it down. In a channel with a constant slope. So we don't want any changes in the channel geometry or a slope, because if that is the case, everything will change. We're going to assume everything is the same, constant slope, constant roughness. We haven't talked about roughness much. We're going to start doing that soon. But roughness, as you can imagine, directly impacts your shear stress. So roughness, we don't want roughness to change either. And constant width, because again, if width changes, then there's no reason for depth to be the same. So constant width, okay? what happens is we just saw, I'm going to write it here, tau times L will be equal to W sine theta. What is this showing us? What is it telling us? It's telling us that the flow will reach kind of an equilibrium in which the driving force, weight, will be balanced by the resisting force, tau L, which is friction force. So flow will reach equilibrium. Kind of a balance of all forces. And the outcome is that, one outcome is that velocities will also be the same. So what does this mean? It means you're traveling with the flow, but velocity doesn't change. This is a good case to compare this to a similar situation in physics. I'm going to sketch a tiny sketch up here in the left corner. If you have an object and you drop it off of a, I don't know, cliff or something, right? What happens? It's going to travel in air, and over time there will be two forces acting on this object. One is its weight, pulling it down, and then there's the resistance because of air. And after a little bit of time, it will reach equilibrium, meaning that its velocity won't change with elevation. That's exactly what we're looking at here. Velocity doesn't change with flow because we have reached a uh, equilibrium. And that is why we can refer to this velocity as the terminal velocity, just like the falling object. So terminal velocity. What does it mean? It's a velocity after equilibrium has been reached, meaning that driving force, weight, is balanced by the um, resisting force, which is friction. Okay, so if V1 is equal to V2, that means we have no acceleration, because if velocity doesn't change, acceleration will be zero. And everything else is constant, discharge is constant, width is the same, slope is, everything is the same. As a result, Y1 will also be Y2. What does this one mean? This one means that you're traveling with the flow, but depth doesn't change. We know that already from a definition of uniform flow, but let's look at it in a kind of a different perspective. So what does it mean? So we have this section, longitudinal section of a flow, and we are going from 1 to 2, that's our water level, and we have a depth of Y1 upstream and a depth of Y2 downstream. And if Y1 and Y2 are equal, what does it mean? It means free surface, water level, water surface, is parallel to bed. That's what it means. If the depth doesn't change, it means distance from the free surface to the bed doesn't change, which is depth, right? Now, this depth that is constant in uniform flow, we call it the normal depth. Normal depth. Or sometimes you see some references call it the uniform depth. The same, exact same idea, just different terminology. Okay, so what is it? It's the fact that y1 is equal to y2 in here. And sometimes we use a notation called y sub n, or y sub 0, or something like that. But it's the same thing. It's the uniform depth of the flow. Okay, so far we really just came up with some definition, some terminology, terminal velocity, uniform flow, normal depth, and uniform depth, the same thing, and so on, right? So we're going to start looking at uh, application to a open channel flow. But before we do that, a couple of things we need to discuss, a little bit of geometry and calculus, very, very, very simple ones, okay? So let's do that before we come back to our open channel flow. All right, let's say we have a channel, okay? That's our channel. And we're looking at a reach of this channel, which is this much. Let's call it L, capital L, right? And the channel has a slope of this much. As you travel delta x, you go down by delta z. That's defined as a slope. And this angle is theta. I'm going to start by looking at mild slope. So in a channel which has the slope is not too much. It's not super steep. Why do we do that? Because it's very common, especially natural streams. I think I've said that before, or tend to be relatively mild. Not all of them, but in most cases. So very, very common. Okay, so let's look at this. How do we define the slope? The slope is equal to, let's call it S, capital S, and it's equal to change in elevation delta z divided by distance delta x. And from calculus, we knew that this is equal to tan of theta. Nothing complicated so far, right? Now I'm going to say we're looking at small slopes. So for small theta, what do we have? If theta is small on my sketch, if you look at it, if theta is relatively small, we can assume that length of the channel is almost equal to distance in the x direction. They're not exactly equal, but they're very close if theta is small. Okay, that's good. So let's go back. Sine of theta. Let's look at sine of theta now. So sine of theta is what? It's equal to opposite, delta z, divided by the hypotenuse, which is L. And we just said L is very close to delta x if theta is small. So we could approximate this and say this is almost equal to delta z over delta x. And we know that this is already tan of theta. So what is the conclusion? If the slope is small, if the angle is small, theta, sine and tan are very close. We can, for practical purposes, you can interchangeably use them. All right, so that's one. Let's go back and continue this and look at a slightly different perspective now. Now, I'm going to say if we have a right triangle like this is theta, and we have an arch, we have a length of this much, and this is L. The length of the arc is L, height is H, it's right angle, and hypotenuse or radius actually is R. Okay, by definition, we know that theta in radians is defined as length of the arc L divided by radius. That's just definition. Okay. For small theta again, for small theta, what do we have? As theta gets smaller and smaller, as you can see on the sketch I have, L will get closer and closer to H. And we already know that H is equal to radius times sine of sine theta. Okay, hold on. Sine theta. That's H. R times sine theta. Okay, so let's do a little bit of calculus here. Let's plug it back into the equation we have above from here. So theta will be equal to L, which is almost equal to R sine theta divided by R. That's definition of theta in radians. And this will be almost equal to sine theta because R will cancel out. So what is the conclusion? What do we get here? The conclusion is that for small theta, for the small slopes, if the channel slope is mild, tan of theta is equal to, not equal to, actually, let's be accurate, is almost equal to sine of theta, and this is almost equal to theta itself in radians. So that's a big conclusion we have here. Okay, so not really related to open channel, just some calculus, some geometry, really. That's what it is. Okay, keep this in mind. Okay, we'll come back and use it in a couple of slides. Okay, keep this in mind. Another side note, the wide channel approximation. I think we briefly mentioned it last time, but we didn't get into too much detail of this. What is this? What does this what is this talking about? So if you remember for, in this case, rectangular channels, if the width of the channel is this much, is B, and the depth is Y, right? We look at this as the ratio of B to Y, and that's an indication of how much sidewalls, the banks really, can potentially impact the flow in the center line. If you have a very wide channel, as you can imagine, like the bottom image, the sidewalls are almost doing nothing to this to the central line of the flow, right? And again, that is an important thing because from practical standpoint, many national streams are wide. They have a pretty wide cross section. Okay, but what does it mean, and what are we looking at, and what are we talking about here? So for a rectangular channel, if you remember, A area is simply B times Y, nothing too complicated. That's the area. The wetted perimeter, again, this is something I discussed in the previous lecture, so if you have missed it, please go watch the video. But the wetted perimeter is this length, and it in a rectangular channel, it will be equal to P will be equal to 2Y plus B. Okay. The hydraulic radius, again, another definition, hydraulic radius, typically we use capital R, is equal to A area divided by P wetted perimeter. In this case, rectangular channel will be equal to BY divided by B plus 2Y. Okay, okay, that's just definition. We've seen that before. Now, if B over Y, width of the channel divided by depth, is equal to 15, what happens? Okay, then hydraulic radius will be equal to, look at the equation I have on the left, will be equal to, I'm going to write everything as a function of Y. Will be Y times 15Y. B is equal to 15Y, right? And the denominator is 2Y plus 15Y. Or this will be equal to 15 over 17 times Y. In other words, R will be almost equal to 90% of depth. Okay, so what is the point? So what this is telling us is that as the channel gets wider and wider, the hydraulic radius gets closer and closer to depth. That's what it's telling us, right? At 15, it's 90%. As B over Y gets bigger than 15, this will be even closer to Y. It might be 95, 98, 99, 99, 99, and so on, right? So, so what is that, and how does that help us? The hydraulic radius will show up in a few equations in the next few slides and our classes. And it's typically a little bit complicated to calculate because it has area and it has wetted perimeter and so on. And especially for non-rectangular channels, it's not straightforward. It's not easy to calculate. But this is telling us that if the width of the channel is super wide, and what does that mean? It means starting at 15, you're 90% close to depth. So you can assume that your hydraulic radius is almost equal to depth and use it and make life a lot easier because calculations will be much easier, right? So that's what it basically is telling us. And as I said, in reality, for natural streams in particular, this is the case. So I'm going to write it here for large B over Y, hydraulic radius approaches Y. So we can make this assumption and say R is almost equal to Y. And as I said, this is the case in most natural streams, which is good news because you don't have to deal with a hydraulic radius in an irregular channel, which is a natural stream. Okay, so that's another kind of side note we had on our uh, kind of calculus geometry almost type setup, right? So let's go back to our equations and open channel flow, and let's look at that. So let's say we have an open channel flow, okay, and the flow is going from left to right, and we have a reach of this fluid, of this flow, and let's say the length is L, okay, and it's a mild channel. The slope is not too large, so I'm gonna write it here. The slope S naught is almost equal to tan theta. Theta is this angle here. And this is almost equal to sine of theta. And this is almost equal to theta itself in radians. Okay, so what are the forces that we have here? We already know that we have F1 upstream, F1 and F2 downstream, and these two are the same because depth is the same and they cancel out, right? Then we have the weight along the slope, which is W sine theta. And then we have friction along the bed. So something like that. And let's call it tau. And okay, what does this simplify to? What does it look like? So if you remember uh, from our momentum equation, tau times L times P. If you remember, tau times L is force per unit width. But if you look at the section down here, we have to also multiply by P, the wetted perimeter, to get the total friction force acting on the total channel wall. So it will be tau L times P, because that's the surface that tau is acting on, P times L. So that's the left-hand side. Right-hand side, we had the weight along the slope. What is weight? Weight is volume, which will be A times L, area multiplied by length, and multiplied by rho g or gamma, and multiplied by sine of theta, right? So that will be our uh, modified form of the momentum equation, the one that we saw earlier. Okay, and again, what is this telling us? It says friction force. Really, that's what it says. Is friction force left hand side, which is the resisting force, is equal to weight down the slope. Weight down the slope, which is the driving force. Okay, that's good. Let's do a little bit of simplification on this equation that we just found and see if we can get anything new. So let's keep tau on the left-hand side. Okay, tau is equal to, and bring everything to the right-hand side. Right-hand side, we have rho g. Let's not touch it. Rho g. And then we have A. L will cancel from both sides, right? Because it appears on both sides. Then we have A over P. A divided by P. And then we have sine theta. Okay. So tau is equal to rho g. A over P is R, hydraulic radius. We already know that. R times sine theta. Or tau shear stress is equal to rho g r sine theta. For a small theta, if angle slope is small, is the same as S naught. So let's replace it with S naught. And this will be our what we call the resistance equation. It is telling us the shear stress in an open channel flow, if you have uniform flow, will be equal to rho g r S naught. I'm going to write down that R is hydraulic radius, just to make sure we are clear. Okay, the shear stress in a open channel flow is equal to rho g r S naught. if the theta, the slope is small, right? So let's go back to and see what we learned about narrow channels versus wide channels. So if you have a narrow channel, so by is less than 15, tau will be equal to rho g hydraulic radius, let's say RH times S naught. Okay. What if you have a wide channel? Then it will be tau will be equal to rho g. In a wide channel, hydraulic radius is almost the same as depth. And we have uniform flow, so depth is normal depth. So why not? Times S naught. So what does it tell us? It says if you have uniform flow in a wide channel, what do we mean by wide? We know that if P over Y is 15, we are within 10% in terms of hydraulic radius versus depth. Right? So if you have wide channel, then the shear stress on the wall will be equal to rho g times depth, normal depth, times slope. Okay, so far we just developed a bunch of equations, really looked at these. So this was mostly theory, right? We didn't really look at practical or measurements or experiments or anything, right? A couple of people looked at this and tried to, convert this to a more practical way. One of them is a French scientist, Chezy, in the 1700, and he said, okay, let's look at the equation we saw. Tau is equal to, I'm going to use gamma r s naught. Let's call this equation 1, right? And we know that this is very much close to like a terminal velocity of a falling object. So actually, that's exactly what he did. He said, okay, then it should be similar to a case where you have an object traveling on a slope, right? If this object is traveling down this slope at a speed of v, we know that from drag coefficient, drag equations from physics, we know that the force acting on this will be equal to 1/2 of rho a, projected area, v squared times a drag coefficient called CD. This is from physics, right? So he said, okay, open channels should be very much similar. And he did a bunch of uh, experiments and some dimensional analysis. So dimensional analysis. And the thought that he had was that, okay, just like the object going down the slope, tau, which is force acting on the object, should be proportional to some coefficient, alpha, times rho times v squared. Let's call this one equation 2. The previous one was equation 1, shear stress. Okay, if we combine 1 and 2, what do we get? On one side, we have alpha rho v squared is equal to gamma r s naught. And if you just do the math and move things around a little bit and simplify, we're going to be left with velocity will be equal to g over alpha square root times hydraulic rate times the square root of hydraulic radius times the slope. Right? That's just simple uh, calculations. And then he said, okay, let's this square root of g over alpha, let's call it something. Let's call it v. Let's call it c. So he said the velocity in an open channel flow in uniform condition is equal to a coefficient like c times the square root of r s naught. This is called the Chezy equation. Uh, that's his resistance equation. And so we call it the Chezy equation. And remember, this is all for uniform flow, for uniform flow. And this coefficient that shows up, C, We call it the Shazi coefficient. So Shazi coefficient. Now, as we just saw, if you have a wide channel, in a wide channel, all we need to do is we can replace hydraulic radius with depth. So velocity will be equal to Shazi coefficient multiplied by depth multiplied by slope. So it will be even simpler. Right? Now, one challenge with Shazi equation was the fact that if you look at the equation, that C coefficient that we have, as it goes up, I'm going to write it here. If C goes up, then velocity will actually go up. That's why sometimes this C is really a kind of a smoothness coefficient. It's telling us how smooth the channel is, which might be a little bit challenging to visualize because typically we're talking about shear stress and roughness and friction. So we're really talking about how rough the channel is, not how smooth, right? So that was a little bit tricky and a little bit difficult to understand and follow. But again, very revolutionary study uh, by Shazi. Now later on, someone else. So this is the Shazi equation. Later on, someone else called Manning looked at this and made some minor changes, which were again very helpful. So the Shazi equation, I'm going to write it here. Shazi equation is equal to, or says velocity is c times square root of hydraulic radius times slope. Manning had a little bit of a different approach. So Manning looked at measurements in natural streams. So his focus was on natural channels, natural streams. Unlike Shazi, Shazi mostly studied sewers and that kind of conduits, right? And he used dimensional analysis and compared results to Shazi. And what he found was that that C coefficient that you have for natural streams, you can actually rewrite it as hydraulic radius raised to 1/6 divided by something, let's call it n. And now this n value was called Manning's n. And now this one's actually a roughness coefficient because it's in the denominator. So as n goes up, c goes down, so velocity goes down. So it's actually a roughness coefficient, not the smoothness, which makes, in a way, makes more sense, right? Now, if you take this, plug it back into the equation we have up there, the resistance equation, and do a little bit of simplification, you will end up with V is equal to 1 over N, hydraulic radius raised to 2/3, S naught raised to 1/2. Okay, and this is called the Manning equation. Manning equation or formula in SI. Now, one challenge with um, Manning's formula or equation is the fact that this one that you see here is not dimensionless. It has dimensions, meaning that in other units, if you're using imperial, it will be a different number. It won't be one. So in SI, that's one, but in other units, it will change. Actually, I'm going to change this from equation to formula because some people question that, oh, okay, so then this is not a equation, it's just a formula because how can you have a equation that changes from one system of units to another one, right? Now, if we have a wide channel, nothing changes except for depth replaces the hydraulic radius. So 2/3 S naught 1/2. So this would be for a wide channel. For natural streams, if they're wide, you can simply use this equation and get the get the resistance and velocity and depth. Now, if we take V and multiply it by depth, we get unit discharge, and it will be equal to 1 over n y naught raised to 5/3 s naught raised to 1/2. So uniform flow in an open channel will be equal to, discharge will be equal to the slope raised to 1/2, depth, normal depth raised to 5/3, and then multiply by some coefficient of roughness, 1 over n. And again, this is the Manning formula for resistance. Now, how does this value of n change? So there's a lot of data available, measurements and observations and so on for the value of n. And typically, if you know the type of surface that you're looking at, you can get a good understanding, good estimate uh, of the Manning n value for that stream. For example, this is just an example, but for example, for concrete, typically 4.9 is, sorry, 0.014 is a typical number. As you can imagine, for new concrete surface versus old aged concrete, it will be slightly different, but that's a good average number. Um, as the surface gets smoother and goes down, for example, glass is 0.01, and as it gets rougher, it goes up. For example, for natural streams, you see that it goes up to 0.025 and so on. For the Fraser River, there are a lot of studies that they have estimated and is somewhere within a range from 0.025 to 0.035. So that's a good Manning's N number for streams, right? If you have um, natural river with gradation and so on, there are actually ways to convert oops, convert diameter um, to Manning's N. So, for example, the gradation of your material, if it looks like this, and your D50 is something like this, right? Gradation of the material in natural stream, so 50% finer. There are equations like the one I have on the screen, Strickler equation, that tell you N as a function of D50 for again natural streams, right? So they tell us what N is as a function of D50 or some other diameters, but usually that's kind of different, a little bit of different variation and option that you might have. Okay, what before we move ahead, the Manning equation seems to be an interesting equation, but let's look at it a little bit more detail. So in SI, in the standard system of units, we saw that velocity from Manning was 1 over n. Y naught, let's say we assume it's a white channel, 2/3, S naught 1/2. Okay, let's do a little bit of a unit dimensional unit analysis. Left hand side we have velocity, so velocity is m0 L1 t negative 1, right? Right hand side we have 1 over n. I don't know what the units are. I'm going to keep it as is. Then I have uh, depth, which is length, so it will be m0 L 2/3 because it has the exponent 2/3, and then t is 0. And then we have a slope. Slope is dimensionless. It's 5 in 1, 2 in 1, whatever. So it's m0 L0 t0, right? So if you do the math and rearrange this equation, you will see that n will be equal, units of n will be equal to m0 L negative 1/3 and t1. For example, in SI, it could be something like seconds over meter to the 1/3. A very strange unit, right? And that is one kind of weakness of the Manning formula because it's actually not dimensionless. In imperial, so I'm gonna write it here. In imperial engineering units, um, let's say your engineering units, you can actually do the math and figure out. But if you do that, you will end up with a conversion of meters to feet. Second is second, so it doesn't change, right? Time. And then this is raised to 1/3, and this will be a number equal to 1.486. So what that means is that your Manning formula in imperial will be actually n y naught 2/3 s naught 1/2, and instead of 1 we have 1.486. So we need to be careful if you're using a Manning formula in imperial versus SI. We have to be careful that that number changes from 1 to other numbers. Uh, I have a bunch of images now just to give you an idea of what kind of Manning end we're looking at in different rivers, and these are taken from this book. So a bunch of images showing this is New Zealand, but doesn't really matter. Same idea applies to all rivers on the planet. Yeah, this is another reference from USGS. I think I put a copy on Canvas, so you might be able to see that. But anyways, a stream like this, it looks like it's pretty much straight. The banks, we don't see too many big roughnesses. We don't see boulders or big roughness elements. This corresponds to an N value of 2.6. You notice that for Manning's N, it's a lot of visual inspection and kind of looking at the stream and trying to figure out um, what value is the best representative number. This one, there's a little bit of curvature on the banks, and looks like the banks have a little bit coarser material compared to the previous one. And N here is a slightly higher. This one's estimated at 0.035. This next one, you're starting to see some relatively large boulders on the banks, so roughness is expected to go up. This one's 0.43, I think. This one the same. You see a lot of debris and other features, so N is higher. This one's 0.59. This one, yeah, you see that boulders are so big that they're actually protruding out of the flow. And this is a relatively high Manning's N, 0.075. Yeah. So yeah, again, the bottom line is that for Manning N, there's a little bit of visual inspection and a little bit of uh, kind of conversion and comparing to available uh, let's say pictures and so on. But a lot of streams have been studied enough that we have a good understanding of what represents what kind of stream and so on.